Hello, good people. Welcome to topic 6.9. We are continuing our look at antiderivatives, but we realize in this section that sometimes the antiderivative is not as easy as just reversing the formula. And so here in this first video, we're looking at a table that has 5 rules you definitely need to know. Off the top of your head, can quickly recite what the antiderivative of sine u is, that would be the negative cosine of u, plus c, what the antiderivative of cosine u is, and that would be the sine u plus c. The antiderivative of e to the u du would be e to the u plus c. The antiderivative of u to the negative 1, which, by the way, can also be written as the antiderivative of 1 over u du, and that's going to be the natural log of the absolute value of u plus c. And again, we use absolute values to ensure that whatever is inside of the natural log, since we don't know what it is, but whatever's inside is a positive value, because we can only define the natural log of something is only defined if that something is a positive, right? I can't take the natural log of a negative value, but I can take the natural log of a positive value. And so putting the absolute values ensures that whatever u is always going to be positive, and it is going to be possible. And then the last one is the reverse power rule. The integral, or the antiderivative of u to the n, is u to the n plus 1 divided by n plus 1 plus c. And so one of the things I want you to notice, or Brian Passwater wants you to notice, and I agree that we should notice, is, if I can find my form here, where did it go? So one of the things we want you to notice is that all of these formulas are written in terms of u, not of x, right? And one of the reasons we're going to start to think in terms of u is because you're rarely going to see, hey, take the antiderivative of e to the x, right? We know that answer is e to the x plus c. But you're probably not going to see that. You're probably going to see something like, take the antiderivative of e to the pi x. Well, now this exponent, which is normally just a variable, now it's a function of the variable. And so we replace this complicated looking thing with a u. And one of the things, and I guess this is what Brian's telling us here, that we know that the antiderivative of cosine x dx is sine of x plus c, but when I try to take the antiderivative of cosine 2x dx, that's not sine of 2x plus c. This 2 constant being introduced to my integral has now, or my integrand, is now made my answer different. So I can't just do this, right? And we can say, well, why? Why doesn't that work? Well, if you take the derivative of this, if you take sine of x plus c and take the derivative, well, according to the sum rule, that would be the derivative of sine x, which is cosine x, plus the derivative of constant, which is 0, and that is cosine x, right? So that gets us back to where we started. But if I try to do the same thing over here, and I do the sine of 2x plus c, and I try to take the derivative, well, the derivative of this is going to involve a chain rule because I have an inside function. And so the derivative of sine would be cosine with the inside still in it times the derivative of the inside, which is 2, plus the derivative of the constant, which is 0. And that's going to push me to have an answer of this, and that's not what's here. So as we introduce situations where we have an inside function, an inner function, also known as a composite function, composition of functions, then we know we're going to have to try something different. It's not going to be just a straightforward antiderivative. And so this process that we're going to introduce here is essentially the same idea as using the chain rule for derivatives. So whenever we have composition, whenever there's an inside-outside function situation, when we were taking derivatives, we use the chain rule. But now, as we take antiderivatives, we're going to do something called U substitution. And the reality is, I could have picked, or mathematicians could have picked any letter and called it, K substitution or M substitution. But U substitution is the standard symbol to use whenever we're trying to replace an inside function in a composition situation. So we're going to find that the first and most important part in this whole deal is identifying what the u is in the expression. And so we're going to take the time to identify the u in all of our complicated looking integrals, and then seeing if we can apply u substitution to get to the answer. Identifying the u really just means we're looking for that inner function. Brian calls it the junk. The junk is usually stuff that's inside of the parentheses, or a radical, or any grouping symbol, really. It's the inner function. Grouping symbol would be something, like this, or anything where I have an inside. That's probably my junk. That's probably going to be my u expression. The junk is more of a complicated expression, I guess, that we are trying to make less complicated. So whenever you see, for example, in this example that he gave us, this would be my u, because if it was just an x, that would reduce it to this, and I could take that antiderivative, right? So we're looking for an inside function that looks that's making my integral more complicated, and we're going to replace it with this u in order to be able to take the antiderivative using one of our rules that we know how to use. Okay, that's going to be our goal. So here are some strategies. Number one, we're going to have to identify what the u is in each integral that we're doing, and we're going to set the inner function, that junk, if you will, equal to u. It says look for parentheses, look for radicals, look for anything that has an inside. Chances are that's your u. And then we're going to find du. Du is the differential. We're going to take the derivative of both sides of that u equation. And then we're going to substitute u into the original problem. We're going to make sure that we can substitute du, and if we can't, we're going to fix any constants, and we'll get into step 4 here in a little bit. We're going to integrate using one of the formulas that we know. He says use one of the 5 formulas, but you can use any formula that you know that can help you take an antiderivative. And then we're going to substitute back to an expression for x if we're talking about indefinite integrals. So if we don't see any limits of integration, if there's no a and b here values in my integral, then we need to go back to where we started, which was the world of x's, because we had switched our situation to be a world of u. So here's what we're going to do. At the end of this video, I'm going to help identify all of the u expressions in these examples. So we have 6 different examples. We're going to identify the u, and we're going to find du. So we're going to do steps 1 and 2 in this video. In the subsequent videos, we'll continue to practice the rest of this recipe, if you will, to make sure that we can take the antiderivative of a situation where there's an inside-outside function or composition. Okay, so let's begin. In example 1, we want to take the antiderivative or the indefinite integral of 2 sine of 2x dx. So this is not just sine of x, this is sine of 2x. And so I'm going to say that this is my u. So I'm going to come over here to the side and say my u is 2x. Great. Now I'm going to take my derivative. So the derivative of u is equal to the derivative of this, which would be 2 dx. In the next video, what we're going to find is we're going to transform this integral from x's into u's. But I need to know what my u expression is going to be in order to replace that. But I also need to know what my dx is going to get replaced. And I usually tell students, it's kind of like when you go to another country that uses a different currency, a different money system. You have to convert, right? Like if you have US dollars and you're going into Canada, you're going to have to change it to Canadian dollars. If you're going to Mexico, you have to change it to pesos. And there's an exchange rate. This for that, right? And so what we just found is I can replace a du for 2 dx's. So if I have 2 dx's, I can replace that for du, just like I'm going to replace 2x for u. Okay, but we're just identifying and finding the du's. Okay, so let's keep going to example 2. I'm taking the antiderivative, or the indefinite integral, of x squared divided by the square root of x cubed plus 1 dx. Do I have an inside function? Do I have an inner function? And the answer is yes, it's right here. So by the way, by itself, this looks pretty complicated. But what we're going to find is if I can use substitution, I can make it look simpler so that I can take an antiderivative and then I can revert it back to the world of x's. But right now, all we're doing is identifying the u, and then we're finding the du. Du would be 3x squared dx. And that's it. That's all we're doing. That's step number 1 and 2 of this process. Identify what's going to be your u expression, and then take the derivative of that u expression. When I look at number 4, this one's a little tricky because we don't see necessarily an inside function. So I'm taking the integral, or the antiderivative, of 3 divided by 4 minus 2x dx. Where is the inside function? Well, we're going to say the denominator is the inside function. So u equals 4 minus 2x. If that's true, du is equal to 0 when I take the derivative, 0 minus 2, which is just negative 2 dx. Again, this is saying if you have negative 2 dx, you can make a replacement and replace it, substitute a du. Just like if you have 4 minus 2x, you're going to replace that with 1u. Let's look at example 3. Taking the antiderivative, or the indefinite integral, of x times e to the x squared minus 1 dx. What do you think would be the inside function? If you said x squared minus 1, you are correct. But now I need to take the derivative, and the derivative is 2x dx. That's it. That's all we're doing. And then example 5, this might be an obvious inside function because I have parentheses, and parentheses have an inside part. So that's going to be my u, and then my du is going to be 3 dx. So far, so good. Well, I guess you can't ask questions right now, but you can ask them when you get to class. The antiderivative of sine 3x minus cosine of x dx. Do you think there's a need to establish a u expression? And the answer is yes, but only in the first part. And so if I were you, I would rewrite this as the integral of sine 3x dx minus the integral of cosine x dx. We can, since we're subtracting terms in the integrand, this is called the integrand. The whole thing is an integral, but this is the integrand. Since there are 2 terms in the integrand, and I'm subtracting them, I can split them apart and say the first integral minus the second integral. Well, this, we can find the antiderivative of cosine x, but this has an inside function, so we're going to need to do a little u substitution for this part. The derivative of 3x, I'm sorry, du. The derivative of 3x is 3 dx. So we're going to come back in the next video and we're going to continue the process. But again, part 1, what do we do? Well, let's think about the overall picture here. What we're encountering now are more complicated looking expressions that we want to find the antiderivative or indefinite integral for. But we can't use the regular formulas because now there's the whole function inside of where usually there's just an x. And so what we're going to do is establish a u expression that'll take the place of my inside function. And so basically we're doing the chain rule backwards. And we're trying to make it look nicer, simpler, more workable in order to take the antiderivative. We'll come back in the next video and we'll show you the next steps.